The Rubik's Cube. Many people think of it as a toy, or a puzzle, or a measure of self-worth. But actually, it's a calculator. We can use it to do multiplication. For example, let's calculate 41 times 93. First, we'll set the calculator to its default position, which is easy enough. Then we can input 41 using this algorithm, a set of moves that represents multiplying by 41. Similarly, we then input 93 using this algorithm. And here is the result. Let's focus on the front side. We'll look through this list of positions until here, we found a match. This is the 13 position. So that's the answer. 41 times 93 equals 13. And now you're probably thinking, I'm a little thirsty. Or maybe you're thinking, this equation is false. And you'd be right. You should have some water. And also, yes, the true answer is 3,813. But notice, we knew it ended with 13. We got those last two digits correct. The Rubik's Cube doesn't have an infinite amount of positions, so it can't do any multiplication problem, but it can always give us those last two digits. In this video, I'll explain how this method works, and we'll see if we can improve it to get the last 3 or even the last 4 digits. So we're only concerned with the last 2 digits of the output, but that also goes for the inputs. For example, 841 times 293 still gives a result that ends in 13. If we change an input by a multiple of 100, it will also change the output by a multiple of 100, which means those last 2 digits won't change. In mathematics, we call this modular multiplication, and here we're working mod 100. We ignore any multiple of 100. But 100 isn't special. We could do this with any integer. For a simpler example, let's look at mod 5. What should be the 1 algorithm? Well, multiplying by 1 doesn't change anything. 1 times x is still x. So the algorithm for 1 shouldn't change the cube. It's the empty algorithm. Don't make any moves. What about the algorithm for 2? Let's notice 2 times 2 times 2 times 2 is 16. And 16 is 1 mod 5, because it's 1 plus 15, and we ignore multiples of 5. So the 16 algorithm must be the same as the 1 algorithm. It shouldn't do anything. Which means that applying the 2 algorithm 4 times in a row also shouldn't do anything. It should cancel out. So what cancels out if we do it 4 times? A single move. So let's say the 2 algorithm is U. Then the 4 algorithm will be U2, and the 8 algorithm will be U3, or U prime. Then notice 8 is 3 mod 5, so this is also the 3 algorithm. And now we're done. We have the 1, 2, 3, and 4 algorithms. Let's test it. To do 3 times 4, we do the 3 algorithm, U prime, then the 4 algorithm, U2, and we're left with this. And this is the 2 position. So 3 times 4 is 2, which is true mod 5. But we're missing something. We don't have a 5 algorithm, which would also be the 0 algorithm. This is tricky because 0 times anything is still just 0. It creates a black hole that pulls all the other numbers into it. It removes all information. So how could we do this on the cube? Remove all the stickers. Once the stickers are gone, any further moves won't matter. It'll still just be an empty cube. So that gives us a 0 algorithm, and we now have a Rubik's Cube mod 5 calculator. Cool. Next, let's make one for mod 10. 0 still creates a black hole, so it should still remove all the stickers. And 1 still changes nothing, so it should have the empty alg. So what about 2? 2 creates a problem. 2 times 5 is 10, which is 0 mod 10. So combined together, 2 and 5 should remove all the stickers. So maybe 2 should remove half, and then 5 remove the other half? But the other even numbers also go to 0 when multiplied by 5. So should they remove the same stickers as 2? This problem is a little messy, but we can solve it just like we solve 4x4 parity. Pretend it doesn't exist. Seriously, in mathematics it's common to ignore these problematic numbers and just use the nice ones, the ones that don't make 0. These nice numbers are called units. So let's just use the units mod 10. 1, as always, must have the empty alg. What about 3? Well, 3 to the 4th is 81, which is 1 mod 10. So the 3 alg must cancel out after 4 repetitions. And this is just like the 2 alg we saw before. Any single move will work. Let's use u prime as the 3 alg. Then u2 will be the 9 alg, and u will be the 27 alg, and also just the 7 alg. And we're done. That covers all the units. And if we look at the structure of these algs, we see they make a 4 cycle. And the same was true for the units mod 5. And what's more, 2 is 7 mod 5, and 4 is 9 mod 5, so these are actually the same. Using this single system, we can do multiplication in both mod 5 and mod 10. They have the exact same structure. Next, let's see how we can lift this structure to mod 20. First, we should find the units. Anything even is bad. They can make 20, so we'll remove them. And then 5 and 15 are also bad, so we'll remove them as well. But the rest are good. They're units. We have the same 4 units from mod 10, and then 10 plus each of them. So it looks like maybe we can build off of the mod 10 system. And yes, 3 to the 4th is 81, which is still 1 using mod 20. So these algs will still work with these 4 units. We just need to add in the other 4. But how can we do that? It helps if we change the way we're thinking. Instead of 19, we could write this as -1, since 19 is 20 minus 1. Similarly, we have -3, -7, and -9. And now we just have the negative versions of the other units. We just need a way to track if the number is negative or not. Let's make d2 the -1 alg. -1 times -1 is 1, and d2 followed by d2 cancels out. So then the -3 alg is d2u prime. It's just the -1 and 3 alg combined. Similarly, the -7 alg is d2u, and -9 is d2u2, and we're done. This works for mod 20. Looking at the structure, we have a 4 cycle and a 2 cycle. It's a little more complex than mod 10. Now, let's jump to mod 100. 3 no longer works for this 4 cycle, since 81 isn't 1 in mod 100. But 7 does. 7 to the 4th is still 1. So we just need to adjust this 4 cycle to be 7, 49, and 43. The 2 cycle still works the same, except now -1 represents 99 instead of 19. And to complete this, we just add a 5 cycle with 1, 21, 41, 61, and 81. Any unit mod 100 can be made using one number from each cycle. For example, 3 is 43 times 1 times 21. But we still need algs. We need a new alg for that 5 cycle. The -1 alg D2 takes up a lot of space. It moves a lot of pieces. So instead, let's switch it to be this, which just flips these two edges. And that frees up enough room for this alg, which cycles these 5 pieces. Perfect for our 5 cycle. So we'll make it the 21 alg, and then the rest will follow. Here are all the algorithms and positions for all units mod 100. Give it a test. Try a multiplication problem. Alright, with that done, we've arrived at the next question. Can we do mod 1000? No. Mod 1000 needs a 4 cycle, a 2 cycle, another 2 cycle, and a 25 cycle. And we can't fit a 25 cycle onto the cube. If we did, there would be a sticker that visits 25 different locations during that 25 cycle. But the cube doesn't have that many locations. The cube has 6 sides, each having 4 rotations. So there's a maximum of 24 locations. Not quite enough for a 25 cycle. We just barely can't do mod 1000. And even if we use a 4x4 or a 5x5 or any n by n, we'd still be limited by those 24 locations and we wouldn't be able to multiply mod 1000. But we can do this using the Megaminx. It has 12 sides with 5 rotations each and therefore has 60 locations, more than enough for mod 1000. Great! But if we try to take the next step up to mod 10,000, we'd need a 125 cycle, which even the Megaminx can't handle. So we've kind of hit a practical wall. But we don't need to just focus on powers of 10. What if we look at all the integers? The 3x3 can handle any modulus up to 47. Mod 47 doesn't work. It would need a 23 cycle, and even though there are 24 locations, a 23 cycle doesn't work because of some technicalities. However, if we use a 4x4, the centers move freely enough to allow for a 23 cycle, so we can work mod 47. But we quickly run into a problem again with mod 59, which needs a 29 cycle, and that can't fit on any sized cube. And that happens again with mod 81, 83, 101, 106, and as we climb higher it gets harder and harder to fit onto the cube. Despite this, there are some big numbers that do still work, like 120,120. We can use just one normal 3x3 to do multiplication mod 120, 120. Why does this work? Well, it has a lot of cycles that are pretty small. And it's actually the smallest number that's represented by 7 cycles. And that's because it's the product of the smallest primes. But why is there an 8 instead of a 2? And how do we find these cycles? In my following videos, I'll discuss how we can find the structure of modular multiplication and explore the patterns of numbers with a lot of small cycles, just like this one.